Physics rarely asks you to just memorize a formula. It asks you to look at a car accelerating down a highway or a force pushing an object at an angle and use mathematical tools to predict exactly what happens next. This graph shows a displacement time curve. To know how fast the object is moving at any specific second, you need the slope. That is exactly what differentiation does. By taking the derivative with respect to time, you instantly find the velocity. Let's look at a classic NEET 2006 problem. A particle moves along a straight line according to the equation x equals 40 plus 12t minus t cubed. To find how long it travels before stopping, we first find its velocity. We use the power rule. Multiply by the exponent, then subtract 1 from the power. The constant 40 becomes 0, 12t becomes 12, and t cubed becomes 3t squared. Our velocity equation is v equals 12 minus 3t squared. The problem asks when the particle comes to rest. Physically, that means the velocity is 0. We set our derivative to 0 and solve. 12 equals 3t squared, which means t squared is 4, giving us a time of 2 seconds. To find the distance traveled, we plug 2 seconds back into the original displacement equation. That gives us a position of 56 meters. But remember, the particle started at t equals 0 at the 40-meter mark. Subtracting the starting point from the final position gives us a total distance traveled of 16 meters. Calculus allows you to take a static equation and extract the exact speed and stopping distance of a moving object. This chart shows the exact opposite process. While differentiation breaks things down to find a rate of change, integration adds infinitely small pieces together. Visually, integration calculates the total accumulated area within these shaded regions between the curve and the x-axis. In physics, if you push an object with a constant force, work is simply force times distance. But if your force changes as you push, you graph it. The area under a variable force displacement graph equals the work done. To calculate that area, we integrate. Let's solve the integral of 3x squared plus 2 from x equals 0 to x equals 2. We use the integration power rule. Increase the power by 1, then divide by that new power. 3x squared becomes 3x to the third over 3, simplifying to x to the third. The constant 2 gains an x, becoming 2x. Finally, we evaluate our limits. We plug in the upper limit of 2, which gives us 8 plus 4, or 12. We subtract the lower limit of 0, which is just 0. The total energy transferred by this variable force is exactly 12 joules. Whenever a force fluctuates over time or distance, integration is the required tool to measure the total work accomplished. When objects move or forces act in 2 dimensions, simple addition fails. You have to account for direction. The triangle law shows us that to add vector b to vector a, we make the second vector start where the first one finishes, connecting them head to tail to draw our resultant vector. To find the actual numbers for this new vector, we rely on right triangle trigonometry. By looking at the angle theta between the original vectors, we break vector b down into perpendicular components, b cosine theta along the x-axis and b sine theta along the y-axis. Those components feed directly into 2 vital formulas. We use the Pythagorean theorem to find the magnitude of the resultant, and we use the tangent ratio to determine its exact physical direction. Let's apply this. Pause the video. If vector A is 6 units, vector B is 8 units, and the angle between them is 30 degrees, calculate the resultant magnitude and the new direction angle. Plugging those values into our formulas gives us a magnitude of 13.53 units. The direction, tan alpha, calculates out to 0.3095 relative to vector A. You will use these vector rules constantly because real-world forces rarely push in a straight line. Multiplying vectors is entirely dependent on geometry. You get a very different result depending on whether the forces are working together in the same direction or interacting perpendicularly. When calculating work, we use the dot product. This tells us how much of the pulling force is actually acting in the direction of the movement. Because it relies on the cosine of the angle, the result is simply a scalar number, a magnitude with no direction. Torque, however, requires the cross product. Turning a lever relies entirely on the perpendicular force, which is measured by the sine of the angle. This calculation generates an entirely new vector. Following the right-hand rule, if your fingers curl with the rotation, your thumb points straight up, indicating the direction of the new vector pushing into or out of the page. Take a screenshot of this summary sheet right now. It contains the essential trigonometry, vector laws, and calculus rules you need to have memorized. By internalizing these basic mathematical tools, you possess the specific mechanics required to solve the most difficult numerical problems you will face in physics.